Hi everyone, welcome back to Lulumath. In this video, we're going to take a look at what happens to our domain and our range when we look at real life examples. So you'll need to know about domain and range, and there's a video on that at lulumath.com as well as the Lulumath YouTube channel. And you'll also need to know key features of quadratic relations, specifically how to find the roots and the vertices. So we're looking at this example. While standing on top of a building, Claire threw a ball in the air. The height of the ball y in meters is represented by the equation y equals negative 4.9x squared plus 19.6x plus 18, where x represents the time in seconds. So y represents the height. So we want to know, what are the domain and range of this scenario? Well, let's get a quick sketch going for what's going on in this example. So we know that x represents time in seconds, and we know that y represents the height in meters. We also know that this 18 is our initial value because when we learned about quadratics, we know that the C value is the starting amount. So we know that the ball is thrown initially from a height of 18 meters. We know that the ball is going to start at a height of 18 meters. It's going to go up until gravity starts to bring it back down, and then it's going to hit the ground. So my question is what values of x are going to work here and what values of y are going to work? Well, first of all, time can only be positive or zero. Time cannot be negative. And because the ball will eventually hit the ground, the ball is not going to go below the ground unless there's a hole there, which we're assuming there isn't. So same thing with the height cannot be negative as well. So right there, we are restricted to only non-negative values, 0 and above, for x and for y, for domain and for range. But we also know the ball is going to reach a maximum height. And it's not going to go any higher than that. So that's going to give us our top value for our range, as high as our y values are going to go. And we also know that the ball is going to hit the ground eventually. So we don't model the path of the ball past when the ball hits the ground. So this is going to be our maximum time, or our maximum x value. So now we just have to figure out what these values are. So for starters, let's find our roots. And if you see here, it appears that we will have a negative root that we aren't even going to care about because, again, our time has already been restricted from 0 on. So let's find our roots. Now, if you remember, there are several ways to solve a quadratic equation. We can solve by factoring, we can solve by completing the square, or we can solve by the quadratic formula. Now, I'm not very optimistic about factoring because this 18 is not divisible by negative 4.9 evenly, and I don't want to deal with factoring with an a value of negative 4.9, assuming it's even factorable. So my two options left are to complete the square or the quadratic formula. I'm going to use the quadratic formula, but completing the square will also get you the right answer. So if you remember, the quadratic formula is as follows. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And just a reminder that the standard form of a quadratic relation is y equals ax squared plus bx plus c. So the a value is negative 4.9, the b value is 19.6, and the c value is 18. So I'm going to go ahead and plug in all of this information here. And now I can go ahead and evaluate. So I'm going to leave this as negative 19.6. And I'm going to go into my scientific calculator and I'm going to type in this whole entire expression to get this value. And I end up getting 736.96. And when I multiply 2 by negative 4.9, I end up getting negative 9.8. Well, this tells us that x is either going to be equal to negative 19.6 plus the square root of 736.96 all over negative 9.8. Or x will equal negative 19.6 minus the square root of 736.96 all over negative 9.8. Let's go back to our scientific calculator. And the reason why I'm going to go back to my scientific calculator right now without doing any simplifying is because I can tell that the square root of 736.96 is an irrational number, and I don't want to deal with having to round too early. So I'm going to get to a point where I'm just going to type in numbers that are as simplified as possible without having to do any rounding. So here I'll just type in negative 19.6 plus the square root of 736.96 all over negative 9.8, and I end up getting negative 0.77, and then it's this crazy wacky decimal. So I'm going to say it's approximately negative 0.77. We have irrational roots here. So our first root is approximately negative 0.77. Now let's do the same thing to find out our second root. So I'm just going to go straight up in here. That's the beauty of Desmos. And I'm just going to delete the plus sign, put in a minus sign, and then I get 4.77 as my other root. So x is equal to approximately 4.77. So looking back at our graph right here, we know that this value right here is negative 0.77, but again, we don't really care about that one. It's this one we care about. The ball hits the ground at 4.77 seconds. So that tells us that our domain is restricted to from 0 to 4.77. So we only care about what happens in this area right here. Now for our range, we have to find our vertex. So we have a few options. We can either average our roots, or we could use x equals negative b over 2a, or we can get it from having completed the square because that puts us in vertex form. So because my roots are irrational, and because I haven't completed the square, I'm going to go to x equals negative b over 2a. And here we know our b value is 19.6, and we know our a value is negative 4.9. So we can fill in here negative 19.6 over 2 times negative 4.9. Well, this turns into negative 19.6 over negative 9.8, and when I divide that, I end up getting 2. Now, because our equation is y equals negative 4.9x squared plus 19.6x plus 18, I need to determine what the corresponding y value is. So every time I see an x, I'm just going to replace it with this 2 that we got when we found out our axis of symmetry. So this 2 right here is our axis of symmetry right here. So I will replace the x with 2. Well, 2 squared is 4, so I end up getting y equals negative 4.9 times 4 plus the 19.6 times the 2 plus 18. So negative 4.9 times 4 is negative 19.6. 19.6 times 2 is 39.2 plus 18. When you add it all together, you'll end up getting 37.6. So that tells us that our vertex is the point 37.6, which means that our y values that we are going to look at are just simply from 0 to our highest point right here and just what's in between here. So if our domain is from here to here, we can say that our domain is x is an element of the reals such that x is between 0 and 4.77. We can also say from 0 to 4.77 as follows. It technically isn't exactly equal to 4.77, but for the purposes of real life, we can say at 4.77 seconds, it hits the ground. And then our range is from 0 all the way up to our maximum height of 37.6. So our range is equal to y is an element of the reals such that 0 is less than or equal to y is less than or equal to 37.6, not the 2 because this is the x value, or we could say from 0 to 37.6 inclusive, and this is an exact answer, so it's not as tricky with this 37.6. And these are our values for domain and range that are restricted by the real world. So if you see, when I plug this graph into Desmos, I don't really have a good picture of what's going on. So what we're going to do is we're going to restrict the domain and the range so we can have a better picture of what's going on in our graph. So I'm going to adjust my x-axis to go from 0 to, we know goes to 4.77, so we'll say it goes to 5. And you know what? We'll say from -1 to 5 so we can see the y-axis. And then for our y-axis, we'll say it goes from -1 to, let's say, about 40, even though it only goes up to 37.6. So if you see here, we have this root that we don't really care about, this -0.77. We have our y-intercept of 0.18. We have our maximum of 2,37.6. And then we have our 4.77 where the ball hits the ground at 4.77 seconds. Now, what we can do is we can actually restrict the domain in Desmos so we only see the path of the ball where we want to see it. We won't get any negative values at all. So I'm going to put a set bracket right here, and we're going to tell Desmos that I only care about the x values from 0 to the 4.77 that we got as our root. But I'm going to type in this 4.77010277.6 so I get a better picture of what's going on in Desmos. Again, this is still an approximation. It's still a rounded answer, but it's a slightly more accurate rounded answer. And then all I have to do is put in a colon. So we'll do the shift and then we'll press the colon button. And now when we take a look at our graph right here, we see only the path of the ball where we want to see it. And before we end this video, I just want to specify that these restrictions are not just for quadratic relations. Real life can restrict all kinds of functions and relations that we look at, especially if we're talking about time and other types of things that can't be negative. And that's it for this video. If you have any questions, let me know in the comments below or at lulumath.com, where you can find blank or completed notes for this video. If you found this video to be useful, please make sure to share with others and subscribe. Thank you, and we'll see you next time. Bye.